is the derivative for exponential functions. This means your variable is in the exponent, okay? It's not in the base, it's in the exponent. The basic rule says if you have for any function some number a raised to the x power, and a cannot be 0. So for some number a raised to the x power, f prime of x is equal to the natural log of a, whatever a is, times a to the x power. And the natural log of a is always just a number, but you can write it as natural log of a. You don't have to actually change it. Just be aware that ln a is a constant. You're taking the natural log of some number, and that's just another number. Okay? If it should so happen that the base of your logarithm is e, then your derivative is going to be, it really is the natural log of e times e raised to the x. But if you get your calculator and you check this out, your e to the x is right here above your ln key next to the 4. So if you press second and the ln key, you get e raised to the power. So if you take e to the first power, that's just going to be e. But if you take the natural log of e, then that would be e to the first power. And the natural log of e to the first power is 1. So because this is actually 1, then g prime of x is 1 times e to the x, and that's just e to the x. You don't need to do anything else with it. Okay? Now if you remember having a hard time in finite with logarithm rules and trying to memorize, what goes where and all that, we won't be dealing with the logarithm rules so much in calculus. You'll only need those for simplifying things and solving equations sometimes, and we don't really deal with that very much in calculus. So there's your 2 basic exponential function rules. The only other thing that can happen, and it can happen whether the base is e or the base is a, the only other thing that can happen is, let's say that what you have as your exponent is not just an x, but it's some functional expression of x, like x squared plus 1, or 2x minus 9, or the square root of x, or something else being done to the x. This is chain rule. So the way that we take h prime of x is we're going to take the natural logarithm of the base, which is a, which is just going to be a number. Then we're going to have a raised to the f of x power We're just going to keep that. But then we have to also, because this is chain rule, we're going to take the derivative of f of x. So we'll actually have 3 pieces to the multiplication. But that's as complicated as it gets. It doesn't get any worse than that. So in some ways, your exponential function is the easier one to work with than a great many of the others. Even when it's chain rule, it's easier to work with. Okay? Now the best way to do these is to do some examples. The first example I actually did last time that we were here, but I'm going to start from scratch with it and do it again, just to make sure we're all following along. So what we're supposed to be finding is find the derivative of and our first example is y equals e raised to the power 5x. Now because 5x is itself a function, then that means we're actually treating this like it was e raised to some function in x, which means the way that we're going to take the derivative then, because this makes it chain rule, we're going to take y prime is equal to e to the x, which is e to the 5x in this case because the power is 5x. And then we're going to multiply by the derivative of that 5x. And that's just 5. So then that means that y prime, usually we'll write the number in the front because it's a multiplier. We'll say it's 5 times e to the 5x power, and that's it. You're done. So there's your derivative. So let's try a couple of others. This one says find the derivative of s equals 3 raised to the t power. That means s prime is going to be the natural logarithm of 3 because e and 3 are different. So e's the only one that has the natural log of it is 1. So we actually need the natural log of 3 times 3 raised to the t power. And since t is the exponent, at that point we're finished. We don't need to do anything else. If you did multiply by the derivative of t, well, that derivative of t is just 1. So it doesn't change any of this. Okay? So that's all there is to that one. This one, I want you to think through what this thing actually does. That 10 in front is a multiplier. That's all it is. It's a multiplier. It's a coefficient. So because it's just a coefficient, it's just going to tag along. It's just going to ride along in the problem. So we're going to have 10 left in the problem because that's what it does, is it just hitchhikes and multiplies. So then y prime is the number 10 times the derivative of e to the 3x squared. So the derivative of e to the 3x squared, the base is e, so the natural log of e is 1. We don't need to write that down. Times e raised to that power. But then because that power is a function, then we need to take the derivative of that power. 3 times 2 is 6x. So that means our full complete derivative is 10 times 6x is 60x times e to the 3x squared power. Any questions on that one? Anybody?
So you just take the first, the original function and multiply it by the derivative of the exponent?
Yes. As long as the base is e. It has to be a base e. It has to be base e. If the base is not e, then you just take the natural log of whatever the base is and add that right in with everything else. Okay? Don't overthink this one. It would be very easy to overthink things. Okay, now here's one that doesn't have an e. This one says s is equal to 8 times 10 to the 1 over t power. So here, your base is 10. Your coefficient, which is your hitchhiker, is 8. And then your power is 1 over t. And you could rewrite 1 over t as t to the negative 1 power and use your power rule to find its derivative. Okay? So when we start writing this derivative, here's what we've got. We have s prime, which says that, hey, I'm the derivative of s. We let our coefficient just hitchhike, so there's the 8. The derivative of the base 10 is the natural log of 10. And then the derivative of 10 to the 1 over t power is 10 to the 1 over t power. And then the derivative of 1 over t is the same as the derivative of t to the negative 1 power. Okay. So that's going to be negative 1t to the negative 2 power. So there's how everything fits in. So that means that if we clean our derivative up a little bit, and we might want to clean it up a little bit, we can't do anything with 8 times the natural log of 10. I mean, we could take the natural log of 10 and multiply it by 8. We're just going to get a big, ugly decimal number. It's cleaner just to write natural log of 10 than it is to write 14 decimal places. But we do have this negative sign out here. So when I say 8 times the natural log of 10 times negative 1, that's going to be negative 8 ln 10. And then I'm going to convert that back to 1 over t squared. And then that's all going to be, excuse me? Over.
Like the negative 8 ln 10 over t squared?
Yes, that was the next thing I was going to do. And then I'm just going to keep my 10 times 1 to the t power. Or 1 over t power. So then actually, if you wanted to write it up as small as possible, you take your negative 8 ln 10 over t squared times 10 to the 1 over t power. And at that point, you'd be done. You just basically have these two factors. So there's your derivative. This is the step where you did the calculus. All of this is just algebraic simplification.
Why for this one do you multiply the additional thing you got 8 ln 10, 1 over t times negative 1 t to the negative 2? For like example B, that was kind of similar. You only multiply by the original function, or the original
This
thing,
one?
not by the...
This
yeah,
one?
Yeah, why do you have to have 10, 1 over t and negative t to the negative 2?
Because the derivative of t is 1.
Oh, so you would have to do that, but it was just...
Yeah, you really are doing it, but you know that the derivative of t is 1 and it doesn't change anything. But when we look at the one we're on now, you're talking about the derivative of 1 over t or t to the negative 1, and its derivative is not 1.
Right, okay. So
Okay? Any other questions? Those are good questions. Okay, let's try another one. Because the only way to learn these is just practice, practice, practice. Here we've got two expressions. Y is actually a product. We have two different pieces. So y is actually a product function. So remember your product rule. The way the product rule works, you take the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. So this is the first factor. This is the second factor. And it would be easier to write that radical with a 1/2 power. Okay? Now that we have those two, we need their derivatives. So the derivative of 5x plus 2 to the 1/2 power says that you bring your 1/2 power down in front. You drop the power by a half, or by 1, I'm sorry, not a half, so it becomes negative 1/2. Then you take the derivative of what's inside the parentheses or underneath the radical, which is 5 plus 0, 5 for the 5x and 0 for the 2. And that's just going to be 5. And then put back what was in the parentheses. So this is the derivative of the second. That's what goes here. Now, if you want to straighten it up a little bit, you can do that because you know that 1/2 times 5 is 5 over 2 times 5x plus 2 to the negative 1/2 power. Now, if you're absolutely determined to do anything else to it, then the only other thing you can do is move this down to the denominator and put it back under a radical. So that's acceptable, but so is this. So you're going to take e to the x squared plus 1, your first factor, times this. And then we're going to add, because that's what product rule says to do, is to add. And now we need the derivative of the first factor. So the derivative of the first factor is going to be e raised to that power times the derivative of the power. So you need the derivative of the power, which is going to be 2x to the first power plus 0, which is just 2x. So then the complete derivative that I'm going to carry over here and put after the second factor is going to be 2x times e to the x squared plus 1. So there's your derivative. Back out a little bit so you can see it all together. So there's your derivative. So in this case, your derivative, y prime, what you actually need at the very end of this, is going to be e to the x squared plus 1 times 5 halves times 5x plus 2 to the negative 1/2 power plus 5x plus 2 to the 1/2 power times 2x e to the x squared plus 1.
Explain what you did when you went to the part where it says half 5x plus 2 to the negative 1/2 times 5, and then you simplified it.
Right here?
Yeah, I don't get how you got to 5 over 2 times 5x plus 2.
1/2 times 5. Okay?
Okay.
1/2 times. So that's where the 5 halves came from. Okay? This, I just kept it as it was. I just combined the other two just to keep from having to write quite so many parentheses. Because the only reason I simplify something is to make it easier to enter into my math lab without me maybe messing up the parentheses, maybe not closing one or closing one in the wrong place. So I try to get as few parentheses as I can without having to go to making a whole big mess of algebra. Okay? Now actually, if you were to do this problem in my math lab, I'll point out to you that one of the things they're going to look at is that you've got a factor in the first term of e to the x squared plus 1, and you've got a factor in the second part of e to the x squared plus 1. So they would factor that out in front of that big whole thing. But that's not necessary. You don't need to factor out the common factor. It's just fine to leave it in there. And it doesn't make it any easier to write if you do factor it out. It actually is kind of a wash. Okay? Just be sure you go step by step with these. Do not leave out a single step. Anytime you simplify, show me how you did it. Don't do anything in your head. Show me how you did it. Because if I can see what you were thinking and you accidentally added wrong, well, I'm not going to beat you up for accidentally adding 1 plus 1 and getting 3. But if you don't show me that step, I have no idea where that 3 came from. So I need to see what you were thinking. Okay? Now this one actually is an example of something called a logistic function. logistic function is a very, very useful function in business and in nature. One of the ones that's the easiest one for most people to understand is that, let's say you had a deserted island, and on that deserted island where there was no people, no nothing, you introduced 2 bunny rabbits. One boy bunny rabbit and one girl bunny rabbit. What happens pretty soon on the island? Rabbits have babies. They have bunches of babies. And the babies have babies. And the babies of the babies have babies. And pretty soon you have the great-great-great-grandchildren of the first original pair of rabbits having babies with each other. Because rabbits don't care. So after a while, what happens to your island? Well, they keep breeding, and eventually it seems like there's a rabbit every blooming where you look. You can't walk for walking on rabbits. Only now what happens, remember it's a deserted island, there's nothing to kill them off, but bunnies are going to start dying off. Why are they going to start dying off? They're overpopulated and there's not enough food for everybody. Okay? So what happens is in the beginning you've got your 2 rabbits, then your 2 rabbits become 8 rabbits very quickly, and those 8 become 64 very quickly, and those 64 become 1,256 really quickly, all within probably about 3 months. But somewhere, they're growing really, really rapidly, and then suddenly there's less and less and less and less food, so a lot of the baby rabbits start dying, plus some of the older rabbits start dying because they're not getting enough to eat. So your growth rate slows down. So what the logistic function looks like always is it starts out low, it grows really fast, then its growth slows down, and it flattens out. And the place that this flattens out is what's called the carrying capacity. And this is the idea of a limit in this case. The idea of a limit in this case would be as we let X approach infinity, in other words, we let those little rabbits just keep on breeding and breeding and breeding, and time goes on, what happens is eventually they run out of food because this is all the food that there was on the island to begin with. Okay, so regardless of what goes on in the denominator, sooner or later we're going to reach a constant. Your population is not going to continue to grow, it's going to kind of flatten out. So you'll have about as many births as you do deaths in the cycle, and the population stays even. Okay? Those same kind of functions work in business. Finger fidgeters. Everybody's seen those lately, right? Were they here a year ago? No. Probably somebody got a brilliant idea about 6 months ago, started making these little finger fidgeter things, and they caught on. So what was basically something that wasn't all that popular, suddenly you can't go in a store and not find finger fidgeters. They're at my checkout in my grocery store, for crying out loud. So the growth is on its exponential rise. Now we got a holiday coming up. People are still buying them. What do you suppose is going to happen though come around Christmas time and after Christmas? Growth's going to slow down. It's already kind of doing it because people are already kind of tired of them. It's like anything else. So they have reached their carrying capacity. Their sales have started to, they're going to be constant for a while. Now actually with finger fidgeters, unlike the rabbits, what's going to happen is people are going to stop buying the stupid things, and you're going to be able to find them in the junk stores and the big lot stores for like 25 cents each. And then people are going to start throwing them away because they don't want them anymore. They don't have them anymore. So these are very, very useful functions in business. You'll see these pop up a lot. So suppose we had this logistic function that applied to some product that's being manufactured. We need to find its derivative, because what its derivative is going to tell us is when is it growing the fastest, when does growth slow down, And when does growth come to a standstill and flatten out? All of those are rates of change, which is what your derivative does. So what we're doing when we find f prime is we're finding the rate of change for all values of x in f of x, knowing that sometimes that rate of change is going to be positive and very steep. Sometimes that rate of change is going to be still positive but slowing down. And at some point, that rate of change is going to become a constant, or actually pretty close to zero, because it's going to flatten out. So that's why we even take derivatives, is derivatives give us rate of change, which is slope. So when we take f prime of x, we're actually doing something worthwhile. Now the question becomes then, okay, how am I going to take a derivative of that mess? Because that's a mess. First of all, take into account that this looks like a rational expression. But are there any variables in the numerator? No. So I don't have to do quotient rule. I don't want to do quotient rule. Quotient rule has like 6 different steps in it I have to do. I'd rather do something that doesn't have quite that many steps. So what I'm going to do is I'm going to rewrite the function so that it's not a quotient. I'm going to keep the 100,000, and then I'm going to move all of this to the numerator, and give it an outside exponent of -1. Okay? Because right now it's exponent outside that parentheses is a positive one. When I move it to the numerator, it becomes -1. But now I can analyze my function and know what my different pieces are. That's just a coefficient. So when I take the derivative f prime, that coefficient's just going to ride along. This is a chain rule problem because it has a power on the outside of some parentheses that makes it chain rule. So I use the chain rule to figure out what the derivative of the parentheses is. So that means I'm going to bring the -1 down in front. I'm going to keep the parentheses. So that's e to the -0.3x. And now my -1 out here, I'm going to subtract 1 from it. That's going to become -2. So that means that I've taken the derivative of the parentheses. But now I need the derivative of what's inside the parentheses. I need the derivative of this. Well, that actual part there is easy for the first part of it, because the derivative of 1 is what? 0. It's going to disappear. Plus 100 times e raised to the -0.3x power. Okay, the 100 again, just like this 100,000, is a hitchhiker. What's the derivative of e to the -0.3 power? What's the derivative of e raised to any power? E raised to that power. But am I finished? That's right, you need to find the derivative of the power because the power is an expression in x. It's not a complicated expression, but it's still an expression. So I take the derivative of the power, which is negative 0.3. So now I'm ready to try to clean that up because it does look pretty bad strung out like that. But I have to be careful that I keep the sense of what my parentheses are doing as I go along. But I can also take into account that multiplication is commutative, so I don't have to leave this -1 and this negative 0.3 and this 100,000 as all separate coefficients. Coefficients multiply that whole entire expression. So I can combine 100,000 times -1, which gives me negative 100,000, times negative 0.3, just to be sure I get all my zeros right. $100,000 times -1 times negative 0.3 is 30,000. I don't really need that 0. So that's 30,000 times 100 e to the negative 0.3x. And now I have this part. 1 plus 100 e to the negative 0.3x. And once again, since these are just two things that are hanging out and multiplying, this is a coefficient, this is a coefficient. 30,000 times 100 is 3 million. E to the negative 0.3x times 1 plus 100 e to the negative 0.3x. Now you could actually do a little more multiplication, but that's down far enough to where I'm pretty sure I don't need a whole lot of extra parentheses. So that would be the final form. So this step shows the calculus. This step would be acceptable.
Let me ask, can you not make it do the 1 times that, the 3 million, and just take that out and make it the 3 million?
You can do this, but this is going to be 3 million e to the negative 0.3x plus 3 million times another 100 times e to the negative 0.3 times negative 0.3x. So there's a little bit more algebra involved in it, and I'm not sure it's worth it.
Didn't you not
Yes, you
carry
could.
on that, the -2?
Yes. Where did I leave that out? I left that out up here, so I got to put it back. So this -2 belongs to this. So when I keep it here, it still belongs to this. And that would be a really good reason why you don't want to do that. Because you'd have to square all of this, then multiply through all that. And that would be a mess. Okay? So there's a bonus point for Scott for catching my leaving out my exponent. So this answer is acceptable, this answer is acceptable. This shows the calculus. I want to see that. I want to see that first step, because if you make a mistake in the first step, but I can see where, because of that first step, you carried the rest of it out and did it correctly. If you made a mistake here, I'll try to only charge you for the mistake you made here, not count the whole problem wrong. So be sure and show me every step that you do. I can only give you credit for what I can see. Now, if you can take the derivative of that logistic function, you're not going to run across anything harder than that anywhere. And once again, this is just the usual form of a logistic function. It's almost always an exponential function. This k and this m are just constants. That value of m is also a constant. And a lot of times it shows up here with an initial value. G sub 0 would be your initial value. We'll see that notation again a little bit later. So we're going to wind up talking about product sales, so that we can kind of put all of this in context. So we have a company that sells 990 units of a new product, maybe that figure, and 3,213 units in the fourth year. So maybe not the figure, because it's not going to last 4 years. They expect that the sales can be approximated by a logistic function for the reasons we already talked about, and that it's going to level out at about 100,000 in the long run. So eventually sales are expecting to be around 100,000 units a year. Oops. So the first thing they want us to do is find a formula, S of t, for the sales as a function of time. So when we do that, we need to go back and remember what I told you about these to figure out what we're going to have to plug in. So let's talk through what we plug in. Your initial value is where they started out, 990. That's in their first year. So that tells you that this value of G sub 0 is 990. We know that they expect it to level off at 100,000. Well, that leveling off is the value of m. And m, notice here, shows up in two different places. Now, m also shows, actually it's in three places, I missed one of them. It also shows up in the numerator over 990. This one stays. This e is just the base. T is time, so that's our variable. What we don't know a value for is k. So in order to find the formula we're looking for, we need to be able to find K.
What is the value for T, 4 or 1?
The value of T, T is your variable. It's not a value at all yet, okay? It's the variable time. T is for how much time in years. So it's not actually gonna be a number we're gonna find in here. T just represents time. So we need to find out what K is. Now, if you remember, back when we were first writing the problem, there was a number in this problem we didn't use, and it turns out to be that we need that piece of information to find K. So in order to find K, we know that 3,213 units were sold in year 4. That gives us a point, a particular point in time. So what we're going to use is we're going to use that particular point in time to figure out what K is. And the way that we're going to do that is we know that this is T, and we know that this is G of that particular value of T. So we're going to come down here, we're going to take that information and we're going to let T right here be equal to 4. And we're going to let G of T, or G of 4, be 3213. So before we try to actually solve that and find out what K is, does anybody have any questions about where any of that information came from? Because you have to be able to go from the written problem to plugging it into logistic function. Does anybody have any questions? Okay, so let's see if we can finish up this formula then. This is what we've got as of right now. We know, and I'm just going to scoot this over on top of the rest of it. We know that 3,213 is equal to 100,000 divided by 1 plus the quantity, 100,000 over 990, minus 1 times E to the 4 times 100,000 is 400,000. And that's negative, so that's going to be negative 400,000 times K. Okay? Now, the easiest way to start solving that is to recognize that if we have this as 2 rational expressions, the way you solve for an unknown in your rational expressions is you cross multiply. So we're just going to cross multiply. And when we cross multiply, this is what we get. we get 3213 times 1 plus parentheses. Let's lop off those two zeros, so that's going to be 10,000 over 99. Minus 1 times e to the negative 4,000, I'm sorry, 400,000. K is equal to, because this is the cross this way, 1 times 100,000. Now, rather than trying to multiply all of this together, let's just divide both sides. No, actually, let's just multiply. So let's multiply through times the 3213. 3213 times 1 is 3213 plus 3213 times 10,000 over 99. Let's just eliminate needing to do that. So let's see, 10,000. Okay. And then multiply that by your 3213. And we get 3245.45. It's this times this. It will be this times this, but I think I messed up because I can't multiply that directly. So let me clear that off and start again. I need 10,000 over 990. I know what I did wrong. Minus 1.
Isn't it over 99?
It is over 99. And then I need to subtract that 1.
Actually, when you do 1 plus that and then multiply it all by 32. So it's still be.
No, you can't, because this is the coefficient of this expression. So you can't just combine all of this. Well, let me think about that for a minute.
Oh, I got you.
Yeah, you can't because of that, because actually this whole thing, let me go back to my, this is all the coefficient of e, so yeah, I have to keep that separately.
Yeah, I got that.
Yeah, I actually left out a set of parentheses. I should have actually closed 2 of them right there. This one for itself. Oh, wait, no, not there. One plus that. And that's 3 plus this whole thing. Yeah, the parentheses would actually close out there. So then I actually do need to multiply that. So I'm going to take 1 away from it.
It's 100.
And of course, that's just going to be 100.01. And when you multiply 3213 times that 100.01, you get 321332. 0.45, which is repeating, and we'll probably round that off. And that's the coefficient of e to the negative 400,000 k. And that's all equal to 100,000. And because we've got this on this side, we could subtract this off. So at that point, we have 32, 13, 32.45 e to the negative 400,000 times k is equal to, let's see, what is 100,000 minus 3213? 96,787. So there's where we are right now. Then I need to divide off this coefficient on both sides. Which will get rid of it over here and leaves me with just e raised to the power negative 400,000 k is equal to 0.3012. I think that's probably far enough. 0.3012. So let's get a little bit more paper so we have a little bit more room. So what we have is we have e raised to a power is equal to this decimal number. Now the way you solve this kind of equation, there's actually two ways. You can solve it by putting this in y1 and putting this in y2 and do zoom 0 to let your calculator find the two of them for you. And then based on what you see, you fiddle around with your window till you can see where they cross. But actually the only log rule that you really need to know for this class is how to solve this kind of equation. You remember at the very beginning of this lesson, I told you that the reason we didn't have to, when we did the derivative, that if you take the natural logarithm of e, you get 1, right? So actually what we're going to want to do here is we're going to convert this into logarithms. So if we convert this into logarithms, what it amounts to is that if we take the natural log of both sides of this, the e actually disappears and leaves us with only the power. Because remember, the natural logarithm of e is 1. So it's only going to leave us with the power. And that's going to be equal to the natural logarithm of 0.3012. So what we did here is we took the natural log of both sides. And this is how we came up with this. And the problem is almost finished because now all we need to do is divide both sides by the negative 400,000. And since I've already started approximating, at this point I'm still approximating. So I'm going to take the natural log, sorry, wrong one, natural log of the answer, which is that 32012, and I'm going to divide that result by negative 400,000. So when I do that, I get the number 2.99999. And that e negative 6 means times 10 to the negative sixth power. So here's your actual value of k, or a really close approximation to the value of k. Because I'm going to assume 2.999 is going to be 3. So I'm going to move the decimal from here 6 places to the left, because negative points left. You move your decimal 6 places, and there's the value of k. The value of k is 0.000003. Okay? So now we have to go back to the original problem. This is a little bit long and complicated, but we're going to go back up here because now we know what k is. And now we can write the logistic function, which is what we wanted to do to begin with. So our formula for part A, G of t, or in this case they want us to call it S of t, is equal to 100,000 over 1 plus, for this part, the formula says 100, because this actually comes out to be really, really close, if you notice, to 100. We don't lose anything by just calling it 100. Because it was 101 minus 1, which is 100, times e to the 0.000003 times 100,000, which means we're going to move the decimal back 1, 2, 3, 4, 5 places. So it's going to go back out there on the other side of the 3. We'll multiply it by that 100,000 there. And it was negative, by the way. It was supposed to be negative. I left out my sign at the bottom here. So the value of k should have been negative, because that was negative 400,000. So k is actually negative. And that's going to be 3. And then the only thing that's left is our variable at this point, which is t.
How'd you get negative 3?
Wait, you forgot the 4.
No, that was when the t was 4. That was the initial value we were using here to find out what k was. Now we're going back to being able to find a formula for any value of t. Okay? So we had to use that point from here to be able to find out what k was. All we were looking for was k. We had to go through all that just to find k. So here we've got negative k, which is going to be negative 0.000003 times 100,000, which moves that decimal right back on the other side of the 3, times t. So this is the formula for your product sales. So S of t is how many sales, t years, after introducing the product. So there's our formula. And then what they want us to do for our next step, and we had to find this correctly first, is they want us to find the rate of change of sales after 4 years. What does that mean they're asking us to find? The derivative. And they want us to find it specifically at 4 years. Now, I'm sure everybody in here could take that derivative. But since we're going to have to take the derivative and plug in a number, because you've already done one example taking this derivative, and it was ugly, I'm going to show you a nice way that you can get around having to work quite so hard to be able to finish it up. Go to your calculator, clear off your home screen, go to your y equals menu, and if there's anything there, clear it off too. We're going to type this function in at y1. We're going to have to be careful that we put parentheses where they're needed, or the function's not going to be the right function. So let's talk about parentheses right now. This is your numerator. You don't necessarily have to have parentheses around the numerator. This is your denominator, everything underneath the line. You do need parentheses around that whole thing because it has to do this in the correct order. So you're actually going to be required to have 2 sets of parentheses in your denominator. So our numerator is going to be 100,000 divided by, and then we need a parenthesis, 1 plus, then we need another parenthesis, 100, E, and that's second ln to get your E, and then put in your power, which is negative 3t, or negative 3x. Close the parentheses for the power because it opened them. Close the parentheses for the expression around 100 times e raised to that power, and then finally close the last set of parentheses. If you're not sure if you closed everything, there's the first set, second set. Right in front of that was the third set, so we need to close 3 sets of parentheses. So here we closed 1, 2, now we need to close the third one. Okay? If you open 3, you close 3. So you have 1, 2, 3 that are open. Therefore, at the end of that, you need to close 1, 2, 3. Now that's going to calculate properly. Here's the part that you're going to be very excited about. When you're doing numerical derivatives, go to Math and scroll down.